Okay, so we have derived the OS estimator up to this point. We also have shown that under Gauss markup assumptions, this estimator will produce the best fitted line or plan, in case you have more than just one explanatory variables now, among other lines or plans that you could sketch with your data, right? However, the question remains, how good is that fit then? Now, so for that, we go into the next set of slides. It's called the section 1 and 2 addendum that I put on in Compose. And the first thing we talk about is the good old goodness of fit. Now, and unlike in other sessions, we talk about important things because important to talk about them. Now we will see that it's also important to talk about something not so important. Why is that? Let's see. But for now, let's look at this relationship now. So this is the variance decomposition, the famous one from OS. So it says that the variance of your data, yi, the dependent variables, can be decomposed into two parts. The variance of the fitted value. So by now, we know that the fitted value will equal x times b, right? Not beta, but b, because we fitted it already. Plus the variance of the residual, the error terms. So why there are heads above these variance? Because we're talking about the sample variance now that we calculated or estimated from a sample of data. Now, so from this, we will derive the goodness of fit. Having seen that relationship, we could now ask ourselves, okay, how much of the variation in the data that we have, which is the estimated variance, the sample variance of yi, can be explained by our models. And here when we talk about our models, means what comes out of that, the fitted value. So, and then if you write the numerator 8, the estimated variance of yi itself minus the estimated variance of ei, the denominator stay the same, then it comes exactly to the definition of the R square that we have seen ever since we know OS, right? And we can just plug in the definition of the sample variance of residual and the dependent variables itself in here. However, note one thing that here we use again n-1, not n-k, because at some point we talk about the unbiased estimate of the variance in the sample, we set n-k, right? However, here for this R square, the thing is n-1. I mean, it doesn't matter so much because at the end, these two cancel out, right? Because they both on a numerator and denominator. However, later we also see there's a different kind of R square that use n-k. So it's good to pay attention at this point. Then it comes to the question, what is important and what is unimportant about R square? What did I mean when I say it's important to talk about unimportant things? Now, so first of all, R square by construction, as the formula you've seen on the previous slide show, that it's bounded between 0 and 1 under OS. Now, therefore, it's convenient in a way to interpret it. If it's very close to 0, meaning, okay, the model fits poorly to the data. And if it's closer to 1, then fits very well to the data. And if it's exactly 1, then you have a perfect model with no residuals at all. Now, however, there's no generally applicable rule on what is a good R square. Just because the model fit very well to your data doesn't say that it's a good model, and vice versa. Why? Because remember, the error term captures all the unobservable factors in it that could affect your dependent variables now. So if there's no good way to tease out these unobservable factors, or you don't have the data available, then it is how it is, right? That's the best you could do already. Now, if you just try really hard now to throw variables inside the model just to capture a good R-square, whatever that means, then at the end you may have a very good fit, but the model doesn't say anything about the real relationship of the variables. Yeah? So it has to be justified by theories behind it. That's the point. So I've been using OOS a lot in the last years for my own research, and having learned this thing about R-square, to me it's not really an important thing to look at, but still give me a heart attack once in a while when people ask me why is the R-square so small, and just simply because I don't expect that kind of question anymore. No? So please, for yourself, don't ask that question. No? The first thing. The second thing, if somebody asks you, then ask them what they mean with a good R-square. What do they think a good R-square should be? You much better than that. So keep in mind, there is no applicable rule on what is a good R-square, even though it's one of the most popular things that people usually look at on the output table of the regression now. So also R-square is always highest when using OOS compared to the other estimator. Because why? Because when doing OOS, we minimize this, right? And that is what in the subtracted term in the R-square. So this one is minimized already under OOS, therefore the R-square is always highest when using OOS. Later on, when you see that we in some cases have to use other estimator, then it may be the case that R-square is smaller. However, the alternative models, like the alternative estimators, still have good properties that lead us to prefer them than OOS. Therefore, again, R-square doesn't say anything about whether you have a good model or not. Don't try throwing the ball into the wall until it sticks. To have an awesome model with R-square, but meaningless. Okay, so that's why it's important to talk about an importance of R-square in terms of evaluating a good model. The general thing about it between 0 and 1 does not hold if you have a model with no intercept estimated not by OOS. For example, if you have a model with no intercept, R-square can easily go below 0. And the last point is, one thing we should keep in mind is the R-square just measures the quality of the linear approximation. What we have done so far with OOS, what we have done so far with calculating the variance and integral ratios, just the linear operation. Therefore, it does not tell you anything about the quality of the model. It could well just be that the relationship itself somewhere behind a lot of nonlinearity inside, and we could not capture it. However, OOS is still valid and useful for estimating the marginal effect, the coefficients, which we usually interested in economics, right? And it still serves the purpose And therefore, just the linear approximation doesn't say anything about whether your model is good or not. There are also other alternatives for the goodness of it, not just R square. One of them is the square of the correlation coefficient between the dependent variables and the fitted value of itself. And this is just the formula of the correlation coefficient, and then you square it up raised to the power of 2 y squared, so that at the end it's still bound from 0 to 1, make it easier for interpretation, like I said before. And in the case of OLS, actually these two are equivalent, so they're the same. However, for other cases like OLS without intercept or other estimator, they may not be the same. If the R square can go below 0 for those cases, then the correlation coefficients never goes below 0. So it's more generic in a way. One other issue that we have with R square, you may hear before already, that it will never decrease. The value that will never decrease when you add more variables. Like I said, you can just keep adding many more variables that you could find the data. Even those variables at the end may not be statistically significant in your model, it still can add something to the R square. And then that's one way to go if you wish to have a high R square, but meaningless model, okay? Therefore, there's another measure of the R square targets this issue. It's called adjusted R square, usually denoted as the R square with a bar on it. So what it does actually is replace the n minus 1 on the numerator that we've seen before by n minus k. So it adds a penalty terms in the R square value. How? Because imagine the more variables you have, the less this n minus k is, right? And then consequently, the whole term 1 over n minus k will become larger. And then 1 over n minus k times the sum of square residual will become larger. But then it belongs to a subtracted term. Therefore, your R square will get smaller if you have more variables, right? So therefore, adjusted by the number of explanatory variables relatively to the R square. Because of this nice property, sometimes it's also used to decide whether it makes sense to add one certain explanatory variables in the model or not. So if when you add up variables, your adjusted R square increase, meaning the value it brings is higher than the cost it takes you. The cost here is this penalty term, right? Then it can be considered worth adding. However, this is related to a more complex issue of model specification that we will talk when we come to section 4.